Good morning and welcome to this next lecture on sound and structural vibration. As you can see, we ended in the last class by deriving the non-dimensional form of the coupled dispersion equation. Okay, this is the, let me call this the coupled dispersion equation. Okay. Today we will see what it means and how to solve it. What it means and how to solve it. Okay. Now epsilon I said was density of the fluid, dimension of the duct by mass per unit area of the plate. Now typically this is a small quantity, okay, small quantity in the sense of epsilon is in the range of 0.1 and so forth. Okay. Now epsilon is a small quantity, okay, and I have a certain equation plus a small quantity is equal to 0, and I have to solve for some unknown in here. Now we have seen this in the first problem we saw, the classical problem from Crichton, that when you have a small parameter we use asymptotic methods. Okay, we use the asymptotic method. So again, to repeat, the idea is that if we know the solutions to this particular equation, let me again call it some number, we will call it 1. Okay. If you know the solutions to this equation 1 when epsilon is 0, and this epsilon is 0, if we know the solutions, then if epsilon is added as a small quantity, the intuitive idea is that my solutions here should not have changed that much by the presence of a small quantity. That is the idea. Okay. So if I know these solutions when epsilon was 0, and my query is what are they when epsilon is not 0 but a small quantity, then they should be, the new solution must be a perturbation. That means old solution plus something small. It cannot be hugely different, which makes physical sense. Okay. So first of all, let us see when epsilon is 0 what are we getting. When epsilon is 0 we get these 3, okay, we get xi fourth by omega square minus 1, and we set it to 0. Okay, we put epsilon to 0 and the equation is set to 0. Then there are 3 products, 1 2 3, there are three terms in a product, and so any one of them can be 0. So this can be 0 for example, and this represents the flexural wave solution, wave in the plate, in the 1D plate. We will see that again. Then we have lambda square root of omega square minus xi square, which represents the plane acoustic wave in the duct. Okay. And then lastly the tan lambda square root of omega square minus xi square equal to 0. This is the rigid acoustic duct higher order waves, H I G H E R, higher waves, not getting it here, Okay. So, rigid, acoustic duct, higher order waves. So, there are 3 solutions. So, these are the what I call uncoupled solutions. Okay. When the fluid is bounded by a rigid wall, it behaves on its own. That is the plain acoustic wave and rigid duct higher order wave numbers. When the flexural plate is not in contact with the fluid, that is in vacuum. So, this is the solution. So, these are the uncoupled solutions. Now, when epsilon is brought in, the solutions will become coupled. But further to this, let us see on a diagram what these are. So, let me take an axis. Okay, this is the non-dimensional frequency axis. So, let us look at xi to the power 4th by omega square minus 1 equal to 0, which implies that xi is equal to square root of omega. So, this is the non-dimensional flexural wave in the plate. So, it will look like this. It will look like this. Okay. So, this is the flexure. Next, we have lambda. So, let us say this is 1. Next, we have lambda square root of omega square minus xi square. When that is equal to 0, lambda is dimension, so it is not 0. Then we get xi is equal to, of course, plus minus omega. So, we will take omega. So, xi equal to omega is this plane wave, sound wave, 1D sound wave. Okay. And lastly, we have tan lambda square root of omega square minus xi square equal to 0, and this is the tan. So, what I will say is lambda square root of omega square minus xi square must be some n times pi, right, or omega square minus xi square is some n pi by lambda whole squared, or xi squared is equal to omega squared minus n pi by lambda whole squared, or xi is equal to square root of this thing. Okay, we will take n going from 1, 2, 3, etc. Now, for example, if we take n equal to 1, then my xi is equal to square root of omega square minus pi by lambda whole square. So, pi is a fixed number, lambda is a fixed number. Omega is the only variant in here, omega varies. Okay. So, if omega is less than pi by lambda, so omega is less than pi by lambda, then xi is imaginary. Okay. We have seen that if you have something imaginary, it amounts to a decaying wave. Okay. So, below, for the values of the non-dimensional frequency below pi by lambda, xi will decay away. Xi is an axial wave number. The dimensional form is kx. So, in the axial direction it decays away. So, it is not of interest. Okay. If it decays away a little distance away, you do not pick it up. So, it is not of interest. Whereas, if omega just is greater than or equal to pi by lambda, then xi starts to emerge as a real quantity. That means propagation. That means this wave cuts on, this wave cuts on. Okay. So, the non-dimensional wave number pi by lambda is in the y direction, okay, right, whereas xi happens to be in the axial direction. Okay. From here you can see that xi square plus pi by lambda whole squared is equal to omega squared is very similar to kx squared plus ky squared is equal to k squared. Okay. So, now pi by lambda is non-dimensional wave number in the ky direction. It is related to a shape of the wave in the y direction, okay, because y is bounded on the top and bottom between 0 and a. Okay. So, xi can be propagating, can be non-propagating, and for omega greater than pi by lambda it becomes propagating. So, how do we plot this thing? How do we plot this thing? So, at very large values of omega you can see, because pi by lambda is a fixed number, okay, it does not change. So, at very large values of omega, omega square is much greater than pi by lambda whole squared. So, you can neglect this term and then I get square root of omega square, which is omega. Okay. So, xi equal to omega is my plane wave, right. So, this thing will start somewhere over here, and as time, I mean with frequency it will start approaching, and it will approach the plane wave xi, this is xi equal to omega, the plane wave, but this cut on wave will approach this fellow at higher and higher values of omega. Let me put it in red ink. Okay. So, this is a higher order wave number, but because it has a cut on behavior we call them rigid cut-ons, rigid duct cut-ons. I will use that terminology. Similarly, if I take n higher value, I take n equal to 2 here, I take n equal to 2 here, then I get a higher order cut-on which will start again somewhere here. It will start off vertically and then it will turn and it will start following this plane wave at higher and higher and higher frequencies, and similarly n equal to 3 and so forth. Okay. That means if you decide the frequency is here, your excitation frequency is here, then you take it vertically, then these are the possible waves that can exist. Okay. These are the possible waves that can exist in your acoustic system. That is what it means. Okay. Just a word of caution, what we have plotted is uncoupled. Okay. We use this language commonly. So, these are uncoupled, that means actually when there is a plate vibrating there is no fluid. So, these waves should not be there, okay, because it is uncoupled. Similarly, when these plane wave and higher order cut-ons are there, there is no flexible wall wall is rigid. So, this curve also should not be there, but we use this language. Okay. We plot both of them on the same plot and look at their relationship. Okay. But in actuality what happens, we are going to find the coupled wave numbers, that is the objective. We are going to find the coupled wave number, dimensional wave number kx or non-dimensional xi, we are going to do that. So, then we will plot xi on the same graph, we will plot xi on the same graph to see how they change. Okay. So, these are the three types of waves that exist. The red ones are the fluid waves, the black one is the plate wave. Okay. Now, in the next picture I will give you an idea here of what is going to happen. Again, this is my omega. These are, I am going to uncoupled, I am going to plot them a little light. This is the uncoupled plane wave. Okay. I will show you what I mean by a plane wave. This is xi equal to omega, plane wave. Then the next cut on at n equal to 1, it takes off vertically and starts to curve and asymptotically meet the plane wave. Then the n equal to 2 rigid duct cut on, it takes out vertically too and will start turning, and at higher and higher it will approach this one. Okay. And then we have the plate, okay, we have the plate uncoupled wave number, that also I will plot in a dotted manner. Okay. Now, what happens, when the coupling has occurred, that means now I have a structural acoustic waveguide, fluid couples to the plate, plate couples to the fluid. This picture is going to change. This is the uncoupled picture, but now because they are coupled, this picture will change. So, the question is how will it change, that is the question we are asking. Okay. From the coupled dispersion equation we have with this epsilon quantity, the question we ask is that how does this picture change. Okay. By setting epsilon to 0, this is the picture we got, this is the epsilon equal to 0 picture, uncoupled. But when epsilon is not equal to 0, a small quantity, what does this picture look like? Okay. So, I will give you the story ahead of time. So, let me see if I can. So, there are these extra lines in the middle. I will talk about them little later. There are these extra lines. So, I might need another picture. So, let us see. So, let me take it here. So, I have this red colored acoustic wave. The first cut on, let me say n equal to 1 cut on. So, I will use the language cut on, okay, n equal to 1, and I have the n equal to 2 cut on. Then I have the flexural wave. Let me exaggerate. Let me even take n equal to 3 here. as I said, these are uncoupled and they will approach this plane wave at higher frequency. Now I will give you the picture of the coupled wave just a little ahead of the story. So because epsilon is small, every wave gets modified slightly, okay. There is not a strong modifier to the original wave. So this wave looks a little like this over here. Let me plot. It looks like this, okay, in the coupled case. So let me, I said there are these extra invisible lines. Let me plot them in a light manner. Okay, these extra lines. There's an extra line here. For now, let them be just lines for some convenience. I will give the physical picture meaning later. So now this flexural wave, how does it change? Okay. So there will be a plane wave, the acoustic plane wave will change, get modified. So let me use black. Get modified to this, and then as we approach the flexural wave, okay, it becomes the flexural wave and it crosses at this blue line intersection and it follows the next rigid duct cut-on. So I will show it more clearly here. So this rigid duct cut-on will become this black line over here, okay, and as we approach this flexural wave line, it turns and then it crosses at a certain point. So it is below this frequency, it is below the flexural wave, above this frequency it is above the flexural wave, and then it starts to follow the next higher rigid duct cut-on asymptotically. So this red fellow will become this black line. As he approaches this flexural wave, he turns, crosses at the blue line intersection and follows the next rigid duct cut-on. Okay. So this is the story. So now what happens to this? It will have this behavior, and at this junction, which is coincidence, right? This is a coincidence frequency where the plane wave cuts the flexural wave. There it will turn and it starts following the acoustic plane wave just above. So these black solid lines are the coupled waves. Coupled waves. Okay. So that means what? Now in this system over here, as they are coupled, if I put a pressure sensor in the fluid or I put an accelerometer on the plate somewhere at a certain frequency, at a certain non-dimensional frequency, if I take a vertical cut, okay, I will see this wave, this dark black line and this dark black line. I will see these two waves, or these two waves are possible. Okay. The dispersion equation gives possibility of waves. Okay. In actuality, what will be has to be solved for using a forced problem. Okay. If I force this system in some manner using some piston or something, then we will see what the propagating waves are. That is the actual solution. What dispersion equation does is it gives you this entire set of waves that are only possible. Okay. Whether they will be there or not will depend on the type of forcing you are going to do. So then you have to solve a forced problem, which is a more difficult problem. Okay. So at this frequency, if I draw a vertical line, this is a possible wave, that is a possible wave. Okay. But now these are coupled, so whether you measure it in the sound field or you measure it on the plate, they will pick it up. Both of them are carrying the same wave, they will pick it up, your sensors will pick it up. Or let us say if you shift to a higher frequency somewhere here and I draw now a vertical line, okay, then these crossings, this and this are the possible waves that could exist in your system. And again, if you put a pressure sensor somewhere or an accelerometer somewhere, you will pick up these 3 waves. In either of the mediums, you will pick up these waves. Okay. Now, mathematically, I would like to arrive at these answers. I have given you a schematic picture. Okay. Mathematically, we would like to arrive at these answers. Okay. So now, how do we do that? Another thing, while we are at this picture, let me use maybe blue now. So there is a physical reason why this flexural wave moved upward. Okay. There is a physical reason why this red plane wave moved downwards. Okay. There is a physical reason why at this frequency below you have the wave number below and above the wave number is above the flexural wave number. There is a reason. There is a reason why this black line asymptotically now starts to approach the next rigid cut-on. There is a physical reason why here the plane wave went up, okay, whereas here the plane wave went down. Okay. Now, because the coupled waves are actually small perturbations to the original waves, the language I will use is that I will use the same name but put coupled in front of it. So to me this is a plane wave, this is a plane wave, but now it is a coupled plane wave. To me this is a flexural wave, but now it is a coupled flexural wave. Okay. And I will refer to the region based on frequency. So here I will call it coupled flexural wave below coincidence. Okay. And this I will call the coupled flexural wave above coincidence, okay, between the first and second rigid duct cut-ons. So I will use this language. Okay. We are very close to the end of this half an hour. So instead of starting next section, I will close here. Okay. So we'll start finding the actual mathematical solutions in the next class. Thanks.